Hi, this is Bill.wolf, and welcome to my podcast. I have Ted Johnson with me today. Ted is our Northern Divisional Manager for Eastern Controls.
Thank you, Bill. It's a privilege and an honor. Look forward to engaging discussion about one of my favorite topics, temperature.
Well, there you go. So um, we call Ted Temperature Ted, and the story there is that when I was I'm still one of the salespeople at Eastern Controls, but I was working, and this is years ago, and I went to my boss and I was like, "Hey, Randy," it was Randy Ruth. I said, "Randy, I got this temperature application, blah blah blah," and he goes, "Oh, you got to call Temperature Ted." I'm like, "Who the heck is Temperature Ted?" He goes, "Ted Johnson." Yeah, I said, and I think at the time you're working for SSI, and he's like, "Man, you got to call Temperature Ted. He can solve our problem on that." So that was so Ted has become a legend at Eastern Controls as Temperature Ted. So and we're happy to have him on board with Eastern Controls. Ted's been with us just a tick under 2 years, and Ted has been in the business for 39 years. He's been with manufacturers in major manufacturers in level, temperature, and pressure. He's had various roles: international roles, local roles, management roles, development roles, and engineering. He, before we go into temperature, from a personal perspective, you are a identical twin.
Yes, the joke is I'm the better looking one, but yes, my brother's a accomplished real estate attorney in Delaware, and funny story. Throughout our lives, people have always mistaken us for each other. So his wife has got blonde hair, and my wife has got dark hair. So if she and I were, I think it was the King of Prussia Mall, and then there's a couple that kind of comes up to us, and I've seen this look all my life. The wife has got just dreaded fear in her eyes, and the husband really looks confused. And I look at them both. I said, you must think I'm Dan. I'm Dan's twin brother. And just the relief was overwhelming because over the years, he and I have both recognized that look of confusion. But I've been confused with him in airports and Houston and throughout North America because he does a fair amount of traveling, and so did I. So it
Oh,
was
wow.
it was always interesting. People would come up, "Hey Dan, how you doing?" And you say,
No,
"Oh,
no, I'm not Dan. I'm Ted.
I'm Dan's twin brother." So
Wow, wow. So hey, RTDs and thermocouples. Let's go there a little bit. Through my 40 years in the business, it's like, hey, hey, you know what? I got a temperature application. I'm trying to measure 100 degrees F or 280 F or 40 C or 20 C or whatever. And here's my materials. And we just kind of roll through that on a daily basis. But there's a lot more to RTDs and thermocouples than a lot of us really realize. So let's can you educate us a little bit on RTDs and thermocouples? And I think you're going to go into thermowells a bit and some special applications. And let's just kind of let's do a deep dive on that because the folks watching this, obviously, we should be, I'm sure, have a lot of interest in temperature. So let's go there.
yeah, good point, because temperature is the most measured process variable in industry. And to your point, Bill, it's really kind of basic. Over the years, the general rule of thumb today is if it's below 1,000 degrees, an RTD is your best choice, simply because it's more accurate, it's more linear. The price point for a 12-inch 100 ohm platinum RTD is basically the same as a Type J or Type K thermocouple. So in the old days, RTDs were anywhere from 4 to 5 times the cost of a thermocouple, just because you were dealing with a platinum element, and that was a lot more expensive because of the way they made it. It wasn't until they came up with the thin film RTD element, very similar in concept to microchips with high density wafer etching. You were able to deposit a very thin amount of platinum on the element as opposed to the wire wound, where literally you were winding a thin platinum wire around the substrate and then encapsulating it. So the amount of platinum required in the 100 ohm element is significantly less than the old days, hence the much lower price and the fact that you can now get high density RTD chips made off of a wafer.
Hey, Ted, what time frame was that? Because I think where you're referencing, um, you're right. When I first came into business, it was like, hey, RTDs are much more expensive than a thermocouple. So, what time frame is it that that delta kind of came together?
It basically the early '80s. They really started refining the thin film
Okay.
development and economies.
Okay.
Yeah, so nowadays probably 90% of the RTDs really are thin film, and you use the wire wound for um, more difficult accuracy requirements.
Okay.
And
Um,
just as a kind of a comparison, 100 ohm platinum RTD. When they say 100 ohm, that's because you're putting out 100 ohms at 0 degrees C. If you had 1,000 ohm RTD, that generates 1,000 ohms at 0 degrees C. That's where that nomenclature came from. It's all referenced to 0 degrees C. But to give you a reference point, at um, uh, 0 degrees C, an RTD, a Class B, which is typically the industrial standard, will give you 0.8 degrees C plus or minus,
okay.
which is about plus or minus um, one, well, about a half a degree F, compared to a type J or type K thermocouple, which the accuracy spec on the thermocouple is typically plus or minus 4 degrees or 3/4% of reading. So to put that in perspective, if you're at 100 degrees F, a type J or type K thermocouple could be within spec, and you could be reading 96 degrees or 104.
That's a
Whereas
pretty significant difference.
Exactly. Whereas with a 100 ohm platinum, you're basically, within, less than 3/4 of a degree. Now, it's not until you get up to, say, 1,000 degrees where now you're talking about maybe at 3/4% of reading, it's 7.5 degrees F, where an RTD could be close to 10 degrees just because of that linear error curve on an RTD. So, to kind of summarize, if you're below 1,000 degrees, an RTD is just going to be a better choice. And today, RTDs are outselling thermocouples almost 6 to 1.
Wow, did not know that. And you know what? I just learned something. So whenever I'm talking to a customer from now on, and less than 1,000 degrees F is probably, in my world, 99% of my applications I talk about. So and I have a lot of food processing accounts, by the way, and certainly if they're doing a temperature loop and they're cooking, 4 degrees is a plus or minus 4 degrees is a lot, perhaps on that batch, right? So, okay. Any other thing to add on RTDs or thermocouples, Ted, or do we want to go to thermowells?
Um, just a kind of another quick
Oh,
point. Terms most people historically have looked at thermocouples because, oh, I get much faster response time, and
yes.
you certainly can do that. And where that really shows up is if, like, the general rule in temperatures, the smaller the diameter, the smaller the mass, the faster the response, which makes sense. You've got less metal, less mass for the heat to transfer to register a temperature change. So
Yeah.
to give you a point of reference, in most industrial applications, your sensor diameter is typically a 1/4 inch, or sometimes referenced in millimeters, 6 millimeter diameter sheath. So an RTD, and when they talk about response time, it's the ability to generate a 63.3% step change in reading based upon water transversing across the sensor from ambient to boiling. That's basically the reference to that. Obviously, other industrial applications are a little more difficult to predict what the response time is, but that's what the official standard is. So when you compare one element to another, that's what the standard is. So quarter-inch RTD will give you that step change in about 5 seconds. A quarter-inch ungrounded or grounded thermocouple will be probably close to about 3.5 seconds. So in that reference, there really isn't that big a change. Now, the big difference is if you go with a 16-inch sheath thermocouple, which you can get them down to, in some cases, a 32nd of an inch diameter. That response time is 0.09 seconds. So, and that's typically what you would use in some kind of, engine test stand, or if you're trying to, measure air duct temperature, you go with a much smaller sheath diameter, so your response time is almost instantaneous. But for most industrial applications, particularly if you're using a thermal well, that response issue really does not come into play between an industrial RTD and industrial thermocouple.
So if I'm an engineer or a salesperson working with an engineer or maintenance person, my two questions when I'm framing out that dialogue, or if I'm an engineer looking to specify something, is what kind of accuracy do I need, or is accuracy important to me? And or is speed of response important to me, and what kind of speed of response do I need, and how's that going to impact my process?
Yep.
Cool.
And that kind of leads into the thermal well discussion.
There you go. Yep.
Thermal well, and here's a sample of a threaded thermal well. This design is known as a step down because instead of having a uniform diameter, which is typically known as a straight stem, this has basically got a reduced tip that gets down to a 1/2 inch OD, which is used to get faster response because, again, less mass. So, thermal well design is all based upon, what your diameter is, and particularly if you're going into a pipe with lateral flow, then the wake frequency calculation, the power test code 19.3 comes into play, and most manufacturers have software now that you can program the well geometry, the process data to confirm that insertion length and geometry will survive any wake frequency issues, and you won't snap the thermal well off.
Okay.
So
didn't know that there was that much to a thermal well. I usually always ask, hey, what materials of construction? Hey, let's make sure the thermal well is sized correctly, and we want to have like a spring-loaded RTD or a spring-loaded thermocouple, right, to be able to hit the end, that tip of that thermal well to get that response.
Yep, here's a sample of an element, and again, this could be an RTD or thermocouple because physically they look identical, the same sheath diameter. It's really based upon the number and the color code of the lead wires. I mean, you can basically, with an ohm meter or a multimeter, check whether it's a thermocouple or an RTD, but physically they look almost identical. And here's a case where you can insert it in and use the spring load against the terminal block in the head to make sure you get metal to metal contact. If you've got an air gap, that's a insulator which will reduce your response time and your relative accuracy.
Excellent.
So, the thermal wells are definitely probably one of the more complicated aspects of specifying and designing a temperature loop because there's a lot more that can go into it. Now, the power test code only applies if you're going into a pipe with lateral flow. If you're going in a tank or a reactor, then those calculations don't apply.
Okay. Hey, speaking of a tank or a reactor, I know we were going to go to some special applications, and actually you and I were on a conference call earlier this week with a plant engineer / maintenance lead manager at a little chemical plant I call on, and She had a application for a tank, it was 12 or 13 feet high. She's looking to measure different temperature points across this area. And that was a unique application to me. And I know you've had some unique applications. Can you just kind of go there for a minute? Because again, the folks watching this podcast, they may be a chemical plant person, they may be a refining, power, food, and they've probably got some temperature challenges. Can you just share a couple of those outliers with us, Ted, just briefly here? That'd be really awesome.
Sure. When it comes to temperature, probably the three more interesting aspects are if you had really low temperatures, really high temperatures, and then custom requirements. The one that you're talking about is what's known as a multi-point measurement, where you're looking for multiple temperature points out of a single assembly, as opposed to coming in through the side of the reactor with multiple temperature points. The problem there is it can get expensive. Now you're adding multiple process connections to a reactor that may already be existing that you can't weld and add additional points. So either using thermocouples or RTDs, depending upon the temperature ranges. Most temperature manufacturers can develop what's known as a multi-point, where you can get individual temperature points specified at the elevations, so you can get a temperature gradient measurement, either connecting into a temperature transmitter or bringing back this multiple conductor cable into a thermocouple input card or an RTD input card, or through a temperature transmitter and just going into a analog input card in your PLC or DCS.
Yeah, and if I could, that was important because this company wanted to see if they were trying to maintain a temperature, and if there was a certain temperature delta, they wanted to know that temperature delta, because then that was telling them that, hey, there's something going on with this batch. We could have a bad batch. We need to either shut down, or we need to look at this batch and remix it or reapply. So, and then you had some special alloys applications in the past too. I think you mentioned zirconium one time, Ted.
Yeah, I did it.
And by the way, I did zirconium control valves at one point in my career. So that was a lot of money, and I could even spell the word zirconium on it. So anyway, zirconium, go.
Yeah, it was actually for our friends. And I was at this point, it was a project that we engineered out of Houston for DuPont over in China. A very special reactor where the metallurgy had to be zirconium, and they wanted a multi-point design, one that they could, if they ever had a failure in one of the elements, and I think these were type K thermocouples. So we designed a zirconium, I think it was a 2-inch Schedule 40 welded pipe structure onto a zirconium 600-pound flange, and inside there were individual guide tubes that were welded to the outside of the pipe. Well, from the inside out, inside that Schedule 40 2-inch pipe, I think it was a total of 14 independent elements coming up into a connection head that had compression fittings. So if they ever had a failure during the process, they could literally loosen up the compression fitting, pull out the long or thermocouple element, and then replace it while the process was still running, and do it that way. So that was a very interesting design and commercial success. And I think since we did that first one, they ordered 2 additional ones. So very, very fun. And then probably the last one was some high temperature furnace applications, where it was a incineration process, burning up waste chemicals. So they had to use some platinum elements. That's known as the noble platinum elements, type R, type S, type B, and they required special ceramic glass thermal wells, because virtually no metallurgy would survive for any extended period of time because of the wide range of aggressive chemicals that they were burning. So that was a very interesting. Ended up sourcing the protection tubes from Germany.
Mm.
And that was a very successful application. They tried, you know, Hastelloy, again, because of the elevated temperatures. They're short of, I think the only metallurgy that would have survived, and even then they tried that once, and it doubled the life, but it still wasn't sufficient enough, was tantalum. So again, lots of opportunities with custom metals, ceramics. It's really just understanding what the process conditions are and what the requirements. But it's there's lots of standard applications in temperature, but then again, there's some exciting ones that you can get involved in.
Yeah. So Ted, thanks for sharing that knowledge with us. I know you want to show a trifold sheet that you've done, kind of talks about a guide to thermocouples or RTDs. So bring that up. And folks watching this podcast, I think the message here today is, hey, when you have an application for a really challenging application on temperature, by all means, give us a call at Eastern Controls. And by the way, you know, we have Temperature Ted on our team, so we have got a major resource for temperature. Ted, why don't you talk about this trifold briefly here, and then we'll wrap things up. And folks, by the way, this trifold that Ted is showing, you can give our office a call, ask for one of our inside guys or gals to get it over to you, and or reach out to me in a text or an email, or your own salesperson. You know, so we're here to help you on that. But this is available as a handout or in a PDF document. So Ted, why don't you go there on the trifold real quick?
Yeah, what's nice, it kind of gives you a handy one-place summary. Thermocouples RTDs on the upper left-hand corner, it shows you the color code chart and the accuracy and temperature ranges of all the standard thermocouple calibrations, type J, type K, type T, E, and N. It also gives you the temperature range and accuracy of the premium grade. Most people don't understand that for a little more money, you can get what's known as special limits or premium thermocouples that cut the error in half. And that's based upon the purity from the thermocouple manufacturer. The closer it is to 99.9% purity, the higher the accuracy. And they actually, when they run a spool of MI cable with these calibrations, they do a very extensive metrology test to confirm that the accuracy is within the ANSI and ASTME standards. So, for example, type J, if you get special limits, it cuts the error from plus or minus 4 degrees or 0.75% down to 2 degrees or 0.4%. Mm-hmm. And same thing on the RTDs. If you look at the lower right-hand corner, it gives you the DIN accuracy standard of a Class B or Class A RTD, which, just like with the thermocouples, you can cut your error in half for a slight premium. And again, it's because of the purity of the platinum, as well as some response times here for thermocouples, both grounded and ungrounded, as well as the RTD response times.
This is an excellent guide.
Yep. And then here's kind of a summary of RTDs versus thermocouples. RTDs, best accuracy, long-term stability, no special extension cable that you need for RTDs like you do with thermocouples. So it's really just a handy guide. I use it all the time, just as a reminder. If someone says, "Well, what's the accuracy of an RTD if I'm going to be at 200 degrees C?" It's here. It's readily available.
Excellent. And again, folks, this is available to our customers. It's we can get you a PDF document on it, or get it in a hard copy, and just reach out to your local salesperson for a copy of this. Or again, I call them guys and gals in our office, men and women in our office, and to support our team. We got a great inside sales team, and again, feel free, if you're my customer, shoot me an email or text, or shoot me a message on LinkedIn and say, hey, give me this. And if you're not my customer, shoot it to me anyway, and I'll get it to you, and I'll copy your appropriate salesperson. So anyway, all kinds of ways to get this information over to you. We're all a team here at East Controls, all working together to help our customers. So I want to thank Ted Johnson, Temperature Ted, for coming on. Ted, thanks very much for joining me today.
Thank you, Bill. It was a pleasure, and look forward to any opportunities that we can help folks with the temperature as well as our other capabilities.
Absolutely. Folks, thanks again for joining us in the in my podcast, and we'll see you again in the future. Take care.